Good morning. Thank you very much for the introduction, and thanks for the opportunity to speak today. My name is Rick Clark. I do work for NextEra Energy in Juno Beach, Florida. Always happy to be in Nebraska, where NextEra has a lot of exciting wind and solar projects, either operational or coming along. So great to be here today. Even more exciting for me is the panelists that we have today, two very compelling speakers. And I think they may be right here. There's Keith, and I see Rob on the phone also. You guys are looking better than ever. Excellent. And I think everybody can see you here very well. We're going to start with Keith. I'll introduce Keith and then Rob. Keith Wipke has been the Laboratory Program Manager for the Fuel Cell and Hydrogen Technologies Program at the National Renewable Energy Laboratory for the last 9 years, and he's worked there since 1993. The program covers all aspects of hydrogen and fuel cells, from hydrogen production with renewables to end-use applications envisioned in the H2 at scale bubble chart that I think a lot of us are probably familiar with. Prior to this role, Mr. Wipke worked in the area of advanced vehicles for 20 years. For 9 years, he has led NREL's participation in the Controlled Hydrogen Fleet and Infrastructure Demonstration and Validation Project, also known as the Learning Demo. It's a technology validation activity that has been expanded to evaluate fuel cell technology for other applications. Keith received his master's degree in mechanical engineering from Stanford. He's the NREL senior representative at the California Fuel Cell Partnership. He sat on the board of directors of the Fuel Cell and Hydrogen Energy Association, and he actively participates in the Colorado Hydrogen Network. So let's everyone welcome Keith. Thank you very much for joining today, Keith. Excellent. Our second panelist is going to be Rob Hanson. Rob is the co-founder and chief executive officer of Monolith, where he leads the development of next-generation technology for producing low-cost, low-emission hydrogen and carbon black, which is an important raw material used in the manufacturing of rubber and plastic. Prior to Monolith, Mr. Hansen served as the global director of product management for Areva Solar, the solar division of the world's largest nuclear company. Rob has a master's degree in mechanical engineering from Stanford, and he's been a guest lecturer at Stanford, UNL, Foothill College, and the University of Saskatchewan on topics ranging from thermodynamics to entrepreneurship. Mr. Hansen also co-founded Euphoria Studios. This is interesting, a 65-employee health and fitness company with locations in San Francisco and Palo Alto. So let's welcome Rob Hanson today. Thank you very much. We're going to begin with just each of the presenters an opportunity to talk about kind of their core work. We'll start with Keith at NREL and then switch over to Rob at Monolith. We'll have some questions from me and then open to questions from the audience. So again, looking forward to this. And Keith, I'll hand the floor over to you.
Well, thanks for the intro and for the opportunity. Even though it's been a year and a half of COVID, this is my first hybrid conference. So I hope it works out okay for you guys on your end. I certainly miss seeing faces and all that, but I'll go ahead and get into it. I'm just going to give a brief intro to hydrogen and DOE's program and NREL's program. So let's see here. So you're probably familiar with, just to review, the current U.S. energy goals are to be carbon-free in the electric power sector by 2035 and to be net zero greenhouse gas emissions across all sectors, including transportation, buildings, industry, and agriculture by 2050. And throughout all that, environmental justice, DEI is very important relative to jobs, manufacturing, supply chain, and really trying to lift all people in this energy transition. So you may have heard the Secretary of Energy back in June announced the hydrogen shot, the first of the DOE's energy earth shots. And in shorthand, it's 111, $1 per 1 kilogram in 1 decade to get clean hydrogen. So over on the left, let me see if I can get my pointer here. Over on the left, you see we're about $5 per kilogram from electrolysis-based hydrogen right now through a combination of reducing electricity and capital costs, as well as making them more durable and reliable. We are shooting to get down to $1 per kilogram in the next decade. And so I already mentioned, here's some of the assumptions going from, say, 5 cents a kilowatt hour down to 2 cents a kilowatt hour from cheaper electrons from renewables and other sources, reducing the capital cost by 80%, and really getting that O&M cost down by 90%. And just a really important point here is that all pathways for clean hydrogen are included. This includes thermal conversion with CCS, advanced water splitting, as well as biological approaches. So if you've been watching hydrogen at all, and I'm not sure how much you guys are kind of being more wind and solar focused, but you obviously know this top one. Low-cost renewables are now available and getting cheaper all the time. However, hydrogen has become a more important part of most countries' climate goals and their energy strategies. And just in the last 2 years, going from June of 2019 up to February of 2021, these bar charts show how much electrolyzer capacity was planned to be installed in the next 10 years. So you can see 2 years ago, only about 3.2 gigawatts had been announced. Just a year later, that had gone up an order of magnitude up to almost 28 gigawatts in that 10-year period. And then just another 8 months after that, it already gone up to 41.3 gigawatts. So each month we go on, there's more and more aggressive announcements about electrolyzer installations. And beyond electrolyzers, there are more investments being made in end-use applications, in hydrogen fuel cells, the distribution network, getting it from point A to B, and then, of course, the production, which is primarily electrolysis. This map shows the United States, kind of a snapshot from June of 2021, and the size of electrolyzers that are either installed or being installed in the US today. Here you can see in Colorado, our NREL site, this is this 1.25 megawatt electrolyzer being installed and should be operational by, if not the end of this year, early next year. So just to give you a size relative. This is a Plug Power one up in New York being installed now. So despite the large number of sites shown on here, they're relatively small, right? You don't see, the largest one is 120 megawatt. We don't have any gigawatt type installations yet. This is the hydrogen at scale bubble chart that was mentioned earlier. And I could probably give my whole talk from this one slide. But you've got energy coming in on the left, going to electricity, or bypassing the grid directly and making hydrogen. Once you end up with hydrogen, you have the opportunity to do transportation fuels, either directly as a gas. We're really focusing on heavy duty transport now, trucks, trains, ships. And then you can also make synthetic aviation or sustainable aviation fuel by using CO2. We'll talk a little bit more about that. You can replace the natural gas from, the hydrogen from natural gas in making oil. You've got ammonia, fertilizer, metals production, chemical industrial processes leading to products, and of course CHP. You can also blend it back into the natural gas grid. And finally, you can actually turn it back into electrons on the grid, doing some time shifting. You really only want to do that if you're talking about longer time durations. Otherwise, conventional storage, batteries, pumped hydro, things like that are quite good. This is a quick example of a simulation that we did in our lab that we are going to be proving out with hardware. It just shows how electrolyzers can be used in conjunction with battery electric vehicles, photovoltaic panels, and other loads as kind of a package, an integrated station connected to the grid. And so the reason why you might do that is you've got solar power coming in during the day. It's a little bit spiky if there's some clouds. You have battery electric vehicle charging going up and down. And you can actually use the electrolyzer as a controllable load here in blue, following those combinations of loads and sources to basically give the grid a constant load while providing all these services of making hydrogen, powering your buildings, and charging cars. Just a quick advertisement to some of our capabilities in the lab. We call our electrolyzer fuel cell research from powders to powder. Starting over on the left, we can do material synthesis, electrochemical characterization. We make our own inks, integrate them into MEAs, spraying, we can do roll coating, and then we have evaluation, typically single cell, but sometimes short stack, as well as a manufacturing quality control. I wanted to point out that we are one of many labs working on the hydrogen challenges. In particular, there are 4 consortia that have been launched in the last few years. 2 focused on hydrogen production, really a very important part of the program. One is called H2New, hydrogen from next generation electrolysis of water. We co-lead that with Idaho National Lab. And then there's Hydrogen, which is really focused on the longer term research, going beyond electrolysis to photoelectrochemical water splitting and some other ones. We have one on hydrogen storage. This has really been focused on onboard vehicle storage. It's now pivoting to storage for heavy duty trucks, as well as stationary storage and energy carriers like ammonia or things like that. And then finally, the more recent one is the Million Mile Fuel Cell Truck Consortium, really taking the National Lab expertise on fuel cells and applying it specifically to trucks and trying to get to a lifetime of 1 million miles versus a car, which had only been about 100,000 miles. I just wanted to briefly touch on the electrons to molecules and set up Rob a little bit here. You basically, once you have electricity, low cost or free electrons from solar and wind and potentially storage, you use readily available molecules like nitrogen, carbon dioxide, water, oxygen, and you basically can do electricity-driven chemical synthesis to make intermediates, cause some transformations, either chemical or biological, and ultimately end up with products, low carbon fuels, chemicals, or materials. And Rob will be talking about kind of the material side of that. Here's a real life example at NREL, where we're actually using part of the bubble chart here. We're using low cost, clean electricity coming in, and then we are making the hydrogen. We are putting into this bioreactor, which is this silver tower here, and we are adding CO2 from waste streams, and there are biological organisms inside there that actually respirate methane. They take in CO2, they take in hydrogen, a little bit of sulfur and nitrogen, and they create synthetic natural gas, or we would call it renewable natural gas. Then you can inject that directly into the pipeline. So Southern California Gas has been a huge sponsor of this for the last decade, put in over $6 million into that. We're very excited about there's some patents that have been awarded on this technology. I also talked about the high blending natural gas into the pipelines, blending hydrogen into natural gas pipelines. Just to give you an order of sense of magnitude, the Tesla large battery unit in Australia of 129 megawatt hours is this dot here. The relatively small Rhode Island gas network has a 3,300 megawatt hour capacity. So just to give you a sense of the magnitude of how much energy the natural gas pipelines can store. So this project is a consortium with NREL, Sandia, Pacific Northwest, and Argonne, and then there's over 20 other stakeholders involved. This is a diagram of our site. There's an animation online you can look at afterward. I don't want to spend the time to go through that today. And here's a physical picture of it pre-pandemic. So this picture's about 2 years old. All these rocks over here are gone. And this is now actually our heavy duty fueling area over on the right here. But just to give you a sense of size, here's a Hyundai Tucson fuel cell vehicle and some of our light duty fueling hardware, compression, storage, and here's the bioreactor and all of its balance of plant here. So finally, just wanted to wrap up with kind of a simplistic view of our vision for decarbonizing the transportation sector. We talked a lot about the top part of this coming in, renewable electrons, and going through electrolyzer to make hydrogen. And then you can actually use that to make synthetic fuels for marine or rail or heavy duty vehicles. Really, the light duties will probably be dominated by battery electrics. However, this is kind of the dominant fuels. We do expect that there will still be hydrogen being used all across these different applications. And then finally, a picture of our new capability being installed up at the Flatirons campus, just south of Boulder at NREL. I mentioned the 1.25 megawatt electrolyzer, compression, 600 kilograms of ground storage. We're actually adding to this another 550 kilograms of metal hydride storage in a recently announced protocol project. And then we have a fuel cell, 1 megawatt fuel cell that does allow us to go back to the grid or to another DC load. And that's all I have for my presentation this morning.
Keith, thanks so much for that information. Exciting to see all the possibilities that can be done with clean hydrogen and kind of how NREL is advancing that in so many different areas.
Well, thank you, Keith. That was wonderful. And thank you, Rick, as well for doing this, and Anita for kind of setting everything up. I'm really sorry I can't be there today. It's a bit of an irony because our office is literally right across the street from where you all are sitting right now. I just had some travel that I could not get out of, so I'm sadly in a hotel instead of in the room with you, but still really excited to give this talk today. And I want to thank Keith too. I mean, for a lot of us newer to hydrogen, it kind of seems like it just sprung up overnight, but that's not the case. You know, there's been people who have been working literally for decades and really devoting a big part of their career to doing the fundamental work on hydrogen that allowed in the last few years for it really to grow up and you know, become a more mainstream part of the energy transition. So appreciate those people who did a lot of that work. So I'm just gonna give a quick story about Monolith. You know, we're a hydrogen company. It's around the need for decarbonization. So when you look across the kind of entirety of the challenge we have with reducing greenhouse gases, while I think electricity is step one, it's not the whole pie. And it's going to take a lot of different solutions, and hydrogen, I think, is going to be an important one. And this is kind of the Monolith perspective. We think there's at least 3 pillars to the energy transition. Absolutely kind of the table stakes are renewable electricity. So wind, solar, hydro, nuclear probably fits into that as well. And then the second is battery, right? You have to be able to store electrons for some period of time. I think particularly for shifting energy around kind of in an hour-like basis, and also for doing light and medium duty transportation where the cost of, you know, the extra weight due to the lower energy density of battery is not really that big of a burden in the use case. Similarly, the range requirement is much lower than perhaps something like long-haul trucking. And then that's where hydrogen fits in, is there's all these other sectors like heavy duty transportation, aviation, marine, and then getting into the chemicals, steel, ammonia, and then the longer duration energy storage. So that's kind of Monolith's view of the world. There's more than 2, but I'm going to focus on 2. There's kind of, I think, 2 really viable paths to clean hydrogen production. Keith just spoke about electrolysis, which will absolutely play a very big role in this. It's a little bit of just a pure play electron to energy vector in you know, the hydrogen. But there's another one, and that's what Monolith is focused on. It's called pyrolysis. And so this is where you actually are still having a large input of energy as natural gas, whether it's fossil or renewable. And so you're doing that in the case of fossil, big energy shift through time. And then also electricity. And methane and the other hydrocarbons have a really interesting property, and that's if you heat them up to very high temperatures without any oxygen around, the molecules will split into, in the case of methane, solid carbon and hydrogen. And then when you cool them back down, they don't go back into methane. It doesn't back react. And so it's really kind of a fascinating part of the thermodynamics because it allows you to produce hydrogen that is both clean, right? There was no CO2 produced because your carbon is a solid. And then if you do it right and you actually get that carbon out in a form that has utility and thus has value, you can have really good economics. One last note is it takes a lot less electricity to split natural gas per unit of hydrogen. And right, that makes sense because natural gas is kind of up the energy chain, right? Water sits at the 0 state. In the case of natural gas, it's already been lifted by solar energy, right, and photosynthesis up into a higher energy state that thus takes less energy to split. And so that's what Monolith does. We're the world's leader in methane pyrolysis, renewable electricity, natural gas, and you get hydrogen and solid carbon. Probably the big feature, right, is its CO2 intensity. So this is using GREET full life cycle analysis and just showing a few of the different ways for making hydrogen. So steam methane reforming. I do like to point out, right, that the world already makes a lot of hydrogen. We make on the order of $100 billion worth of hydrogen every single year. And it's largely all made in this process, either steam methane reforming, or in some places they reform coal. And it's great, it's efficient, we know how to do it, but it's got a big CO2 footprint. So when you add up all the hydrogen we currently make, the CO2 associated with it is on the order of the CO2 that the country of Germany emits. So if hydrogen were a nation, it would kind of be sixth in the world in terms of its CO2 emissions. You've got a few options. You can put carbon capture, and you can certainly clean up steam methane reforming with SMR probably down to maybe 3, with autothermal reforming maybe all the way down to 1. Electrolysis, if you're using all clean electricity, you can get to 0. And then this is where pyrolysis fits in. It's quite interesting, where if you use fossil natural gas, you end up with a little bit of emissions still, because you have to count the upstream emissions of the natural gas sector. That is getting better over time, but this is kind of current state. You'd have roughly 0.45 kilograms of CO2 equivalent per kilogram of hydrogen using fossil natural gas. But if you use renewable natural gas, you actually go negative. And this is a really fascinating one, where you've actually pulled carbon out of the atmosphere, right? Because if you burn renewable natural gas, you're kind of carbon neutral, right? You're cycling the CO2 through the atmosphere in a short order of time. If instead you pyrolyze renewable or biogas, you've actually taken carbon out of the atmosphere through photosynthesis into a carbohydrate, into a methane in an anaerobic digester or equivalent, and then you split it and you take the carbon out and you sequester it. So it's a really cool application of our technology, and we are working on that right now at our project south of Lincoln. And this is that project, Olive Creek. So this isn't an artist rendering, this is real. This is steel and concrete in the ground, 5,000 tons of hydrogen production per year and 15,000 tons of carbon black production, which is sequestered. Came online last year. It works, and we're now ramping it up to full production. So this is the largest methane pyrolysis facility ever built. It has the largest plasma torch ever built by a factor of 2. And it's just been super fun and exciting to get to build it and now run it. The part that's really important is this part in the middle. This is the reactor. And all the rest of the plant is largely just standard infrastructure. It's carbon black processing equipment and utilities. And so what we're doing next, and we're working in partnership with another great Nebraskan company, Kiewit, to expand that plant into what we call Olive Creek 2. And all Olive Creek 2 is it's taking that reactor from Olive Creek 1, and it's building 12 more of them. So no more scale up in the core technology, it's just replication, or modular expansion, you could say. And then you common up a bunch of the infrastructure. And so this plant's scheduled to come online 2024, 2025. It's currently slated to be the largest clean hydrogen plant in the country, 60,000 tons per year. And what we're doing with the hydrogen here is probably the most important thing you can do with hydrogen, and what we've been doing with it for the past close to 100 years, and that's make ammonia. So ammonia is NH3, and the end's pretty easy. You can separate it from the air, which is mostly nitrogen. The hydrogen's the hard part. And so if you have clean hydrogen, you can make clean ammonia. And that's what the big tank is. We'll convert the 60,000 tons of hydrogen to close to 300,000 tons of ammonia. That's really important for a place like Nebraska, or generally the Corn Belt. Right now we import a huge amount of ammonia into the country and into the region. And so this will produce some domestic manufacturing, and it'll also be clean. And so that's the plan for the first plant. The last thing I'll kind of close on is the job side. So this is maybe the thing that I'm personally the proudest of and get the most satisfaction out of, is actually building those high-paying advanced manufacturing, where you train people, kind of new energy economy jobs. And so Olive Creek 1, which is, like I said, complete and operating, was about $100 million investment, 201 Nebraska jobs, over $20 million of annual labor, and then a big economic impact. And for us, that's just the start. Olive Creek 2 is going to be close to $1 billion expansion. There's going to be a big announcement in early December around the financing for this, which we're super excited about. But it's going to create a whole bunch more jobs. And like I said, these aren't temporary jobs. These aren't jobs that you need to get a second job on the side to make ends meet. These are like lifelong career building, family building jobs. And so we're super excited about that. And we think that that's an important part of the energy transition, is you can't leave people behind. You've got to actually, build the society you want from an employment perspective while you're doing the energy transition. And we're super fortunate to get to play a small part in that. And so those were the operations. In addition, there's the construction jobs. So this is a picture of Olive Creek 1, where we peaked at about 400. Olive Creek 2 will be closer to 800. And then for us, because our number one input is renewable energy, I think many of you know, and many in the room, we've announced with MPPD a search for a whole bunch of new renewable electricity to help power our plant. And so along with building our plant, we are hoping to be able to, in partnership, also expand the renewable energy in the region to supply it with clean electricity. And of course, there's jobs and economic impact that comes along with that. And so I'll just end, I won't read these, but a couple of quotes of two of our really key employees down in Hallam. One case, as they say in Nebraska, boomerang. So we were able to bring someone back who'd been traveling really all around the country looking for work in engineering. And then another was, he saw the plant get built from his backyard as a local and applied, and Jeremy's just been a great employee. So with that, thank you everyone for listening, and back to you, Rick.
Excellent. Thank you very much, Rob, and really exciting to see just down here locally such a large investment in clean hydrogen infrastructure. So that's super exciting. Thank you very much for sharing. Rob, I wanted to follow up with your excellent comments just about the pragmatic. You talked about the jobs element of your very exciting facility located just down the road in Hallam. I wanted to ask, though, in terms of the products that you're going to be producing, like the carbon black and the hydrogen, what do you think will be the first opportunity for people who live and work in Nebraska to actually interact with the products themselves, the hydrogen and the carbon black?
Yeah, let me start on the carbon black side, because this is one that's real today. It's not the sexiest product you've ever heard of, but from Olive Creek 1, we are selling our carbon black material currently. Carbon black goes into all types of things. It goes into car tires, so a third of every tire on the planet is carbon black. It also goes into belts and hoses, goes into plastics, and then it goes into a whole bunch of other, they call specialty applications. And one of the early specialty applications for us that we've been selling to, Rick, actually at a company in Florida, is a company that makes the colorant for mulch. And if you go to any Home Depot in the country right now and you buy black mulch that you might put around your flower bed, it's got Monolith carbon black in it. So that's a really fun one. It's kind of a lower risk one, right? Tires are higher risk. You've got to get your quality just perfect because it's a life safety product. Whereas, mulch, we're also in things like black plastic, whether that's, keys on your keyboard or, garbage bags. And we're just getting into the rubbers, and that'll be a longer process over several years to get full approval. So I think that's the first place on the carbon that will touch kind of people's everyday lives. On the hydrogen side, it's going to be when we turn Olive Creek 2 on and start producing ammonia. And, ammonia is, as people know in Nebraska, absolutely essential to getting the yields needed to both kind of feed the country and in many ways, lots of the planet, as well as in the case of ethanol, produce a lot of the biofuels that gets blended into our fuel mixture. And so that's where you're going to start seeing Monolith's ammonia, pushing back on imported ammonia, and also not resulting in CO2 emissions from the production of it in the process of, getting corn grown, whether it's for food or, for feed or for fuel.
That's great. Yeah, that's the part I'm really excited about, right? Is having an opportunity to just utilize products with a reduced carbon footprint and just have it really be, I think, a seamless part of the way that the American economy moves forward. So that's super exciting. Speaking about hydrogen applications and kind of accelerating those, Keith, I wanted to ask you about what's going on in Washington. A lot of excitement with the infrastructure bill being recently passed, and I know there's some hydrogen-related funding with that. Could you maybe summarize some of the key provisions in the infrastructure bill related to hydrogen and kind of what elements of it you're interested or excited about?
Yeah, so it's actually a little bit overwhelming because of the size of money dedicated to hydrogen in that infrastructure bill that was passed by the House on Friday night, expected to be signed by the president, I think, in the next week or so. So in summary, there's three main aspects. There's $9.5 billion with a B total. $8 billion is reserved for hydrogen hubs. This is at least 4 hydrogen hubs regional around the country. There needs to be one of them that's nuclear, one that's natural gas or fossil-based, one that's renewable-based, and it's at least 4 hubs. So it's not clear whether there will be more than that, could be 8 or 10, but definitely a regional focus on that. That will be, as soon as the legislation is passed or signed by the government, the president, that then becomes law, and an RFP should come out within 6 months and selections within a year. So, potentially $2 billion for each of 4 hydrogen hubs around the country. That will really kickstart a lot of the activities to, connect up hydrogen producers with end users, and then that connecting tissue to move the hydrogen around between those sources and sinks of energy. The other 2 aspects are smaller but still huge. A $1 billion activity for over 5 years for a electrolysis research R&D focus, and then $500 million for hydrogen manufacturing related activity. So there is not as much detail on those activities, but I'm sure that will be fleshed out in the coming weeks as we learn more. So very exciting. Again, I think this is a tipping point for hydrogen. We have never seen this much funding being dedicated by the government toward hydrogen. The last large announcement like this was back under Bush with the Hydrogen Initiative, and that was $1.2 billion over 5 years. So we're talking about basically, 7 or 8 times that in a 5-year period. So very exciting.
Awesome. That's a very helpful summary, Keith. Thank you very much. There is another piece of legislation I think most of us are familiar with, the reconciliation package, or sometimes called Build Back Better. And Rob, I know that there are some hydrogen provisions that have been discussed in that. Can you maybe share some of the key elements that could potentially manifest in reconciliation, and how they would impact the pace of hydrogen implementation?
Yeah, sure. Maybe first, Rick, since this is kind of a public setting, on behalf of Monolith, I'd love to thank both Senator Fisher, who did vote in the Senate for infrastructure, and Congressman Bacon, 2 of Nebraska's delegation who voted in the Senate and House respectively to pass the bipartisan infrastructure bill. So like Keith just said, there's a lot of good things obviously in hydrogen, but of course more broadly also in roads and bridges and the infrastructure that this country badly needs to invest in. On Build Back Better, as it relates to hydrogen, there is something that many people in the room will know very well, which is a PTC/ITC for hydrogen. And it's largely a PTC. So very similar in concept to the wind production tax credit, where every time you generate a qualified kilogram of hydrogen, you also generate a tax credit. And I think they've done a really nice job in crafting it to be, one, technology agnostic. So it's not picking winners and losers. And that's important because that's what allows for innovation, right? There's ways to do hydrogen that I think, as we go through some of the research and development over the years are going to emerge. And so what it's really focused on is you do full life cycle analysis on the greenhouse gas emissions from producing hydrogen. And if it hits certain thresholds, then there's a tiered system of PTC, ranging from, if you get, say, a 50% reduction in the life cycle greenhouse gases to produce your hydrogen, you get a very small credit. And if you go all the way down to reducing it by 95% or more, then you get the full credit, which is $3 per kilogram. I think it'll be great. I mean, we've obviously seen what PTC has done for wind and what ITC has done for solar. And I think it's really using that playbook to try to get hydrogen to a place that wind is now after, 10, 20 years of kind of over time reducing incentive to get it across the gap.
Awesome. Thanks for that summary, Rob. We've got just about 10 minutes left. I did want to open to the floor and see if there were any burning questions that folks had. We've got, I think, a microphone available here if you could raise your hand.
I have a quick question, too. I noticed on the Olive Creek slides they were talking about green hydrogen. Is there a requirement to classify something as green hydrogen, or is it more of a buzzword, and any indication of where things are headed on requirement for it?
Yeah, it's interesting because there's the entire rainbow of colors for hydrogen. I actually like what in infrastructure and in Build Back Better the U.S. has done, which is just to call it clean hydrogen. and then to define clean hydrogen as a threshold for life cycle greenhouse gas emissions, right? Because that's what we care about. We don't care about precisely how something is made, what the feedstocks are. We care about getting hydrogen and understanding how much CO2 on a full life cycle. You got to go upstream to understand that. So we're kind of a big proponent now of the word clean, and then you'll have different colors. I mean, some people call our process turquoise hydrogen. There's blue hydrogen, there's green hydrogen, there's pink hydrogen and yellow hydrogen. But I think the most simple is just to call it clean and make it based on the carbon intensity.
While other folks think about questions, I'll just keep going with a couple on my list. Keith, you mentioned earlier that you thought battery electric vehicles might be the best solution for small passenger vehicles. Can you comment on why that is? And do you expect hydrogen to have a meaningful role in decarbonizing passenger vehicles?
Yeah, I mean, I think it's ultimately about choice, and certainly, where people live and how they use their vehicles is or how they think they might want to use their vehicles is a big part of their choice, right? People buy SUVs with all-wheel drive. Much of the country doesn't need the all-wheel drive part, but they've got it there in case they want to go to the mountains. It comes with a trailer hitch. They don't own a boat or anything to tow, but guess what? It's there in case they need it. Makes them feel good. So, I think hydrogen provides the possibility of having a no compromise substitution for gasoline or diesel. You've got fast refueling time, you have long driving range, you have sustained power output possibilities, and then you fill up in a few minutes and you keep going. You can get close to that with batteries with rapid charging and driving cross country with, for example, Tesla's superchargers, but it's not something you really want to do every day because it's a little bit harder on the batteries. You generate more heat. It's not as kind of a nice neutral process as charging slowly. So, I think it only comes down to choice, and we believe in all the above. Certainly if I could buy a hydrogen vehicle here today in Colorado, I would, but we don't have any fueling stations right now except for our research one. So if I want to buy a clean vehicle, I would buy a battery electric vehicle. So it's really about choice, and also I think about growing out the network. And as we just talked about, I think these hydrogen hubs will provide an opportunity for a lot of new fueling infrastructure for heavy duty trucks as well as cars. And then also the whole other right side of the bubble chart with the industrial applications, the ammonia and steel making and all these things that right now emit a lot of CO2 and are hard to replace with just electricity.
Very good, Keith. We've got one question here from the audience.
Yeah, Keith, in one of your last slides, you pointed out that quite a bit of R&D is still necessary for putting hydrogen into existing infrastructure, I guess, pipelines, blending it with hydrogen. Right now there's, I think on your slide, it said 0 to 30%. OPPD, the Omaha Public Power District, is still in the process of doing its decarbonization, and has a pretty big emphasis on refueling kind of existing stations, gas stations, with hydrogen. So how big of a hurdle is that hydrogen embrittlement, and are we replacing all the infrastructure, or how's that going to happen?
Yeah, I mean, one thing that we don't often think about, but natural gas infrastructure is being, upgraded or replaced all the time, just as gas stations are. And I think, there are possibilities to blend hydrogen in natural gas in today's pipelines up to probably 15% without much concern by volume, and maybe higher if you actually classify the materials and really do a deep dive into that. But ultimately, for the end game where we potentially stop moving as much natural gas around our country and we're moving hydrogen and electricity instead, then you really need some sort of dedicated pipeline that's been designed with that in mind. It's got the materials compatibility. It's got the right pressure, compatibility as well. So I think, this is a transition, but it's not a transition that's impossible, because we are replacing and upgrading infrastructure all the time. It's just a matter of when you do that, do you do it in a way that's compatible with options, or do you stick with the status quo? And I think this is where, some of these government funding activities can really help maybe pay that incremental amount that makes that new infrastructure compatible with new technologies as well as legacy technologies.
Rob, just one last comment from you to follow up on that. Do you think that alternate hydrogen moving technologies other than maybe pipelines, right? Like, for example, ammonia will be an important part of what we do to move hydrogen to the places we need it?
Yeah, I mean, we say this often at Monolith because we have these two products. Carbon black is just about the easiest thing in the world to move. It's a solid at room temperature, it's shelf stable forever, and it's pretty dense. Hydrogen is pretty much the hardest thing in the world to move. So liquid hydrogen, which you've got to go to minus 253 degrees Celsius, weighs 76 kilograms per cubic meter. So that's 7% of the density of water. And that's kind of as dense as you can make it as a pure substance. So I think there's a need for a huge amount of innovation, because if you want hydrogen to play, a double-digit role in energy, you've got to be able to move it around from areas where it's favorable to produce to areas that's needed to be used. I don't have the answers, Rick, but I think it's absolutely is the answer to your question. And I think that's where some of this kind of R&D effort, these hydrogen hubs, are going to let us take a step forward as a country and hopefully leading that same midstream part of the problem.
Yeah, no, I totally agree, right? Pipelines will be part of the solution, but then there'll be other forms and other mediums like Keith talked about, synthetic fuels, ammonia, et cetera, which will enable the mobility and I think also the export to some extent of, clean American energy from pyrolysis derived natural gas and electrolysis, right, to serve new markets with hydrogen. So, hey, I want to thank our panelists today. Thanks, everybody. Let's give them a round of applause. Really interesting discussion today.